Thanks, guys, for coming to this special summer natural language processing seminar at ISI. I'm really thrilled to introduce David Chiang. He's an associate professor in the Department of Computer Science and Engineering at University of Notre Dame, and he works on computational models for learning human languages. He's received multiple Best Paper Awards at ACL and NACL, and lots of grants. He also works in formal language theory and the connection between that and NLP. But you know, that's off of his bio. But I have to say, David is probably a colleague of mine who I've worked with in natural language processing for about the longest, because I first got to know David when I was an undergrad.
That's right.
And he was a grad student. We both
so only Mitch would be longer.
Right, Mitch would be slightly longer. We both took a course by I guess, well, Mitch was not your professor, but on statistical natural language processing, at the new textbook that had just come out in 99 or 2000 or so, right?
Like
and then I was fortunate enough to work with him again when he was a professor at ISI. You know, we had colleagues in common like Ashish Vaswani and Barrett Zoff. Ashish was David's student. Yeah, I've been very influenced by his work in formal language theory, which is near and dear to my heart. And so I'm really thrilled to hear what he has to say and to learn more about what transformers can and can't do. So thank you very much, David.
All right, thanks, John. It's really great to be back. As John or Peter said, please feel free to interrupt me during this talk. It is a theory talk, and there are a lot of slides where there's a lot of like formulas and stuff like this. The last time I gave this talk was over Zoom to a conference in China, and I could not see the audience. I could not hear them. I had no idea how many people were in the room. I went over time, so there was no type of questions, and so it was like talking into the void. So I'm very glad to be in front of living human beings, and please do ask questions whenever you want to make sure we're all on the same page. All right, so this talk is called What Transformers Can and Can't Do, a Logical Approach. This is joint work with various co-authors, Dana Engleman at Yale, Mikhail Cadillac at DePaul University, my colleagues Peter Cholak and Anand Pillai in the math department at Notre Dame, and my student, Andy Yang. And some of this is work that's been presented at conferences. Some of it is under review, and so it's a kind of mishmash of several papers. Okay, so what is this talk broadly about? It's about expressivity of language models. So we're interested. Yeah, I mean, I guess in some ways this is a very old-fashioned research program. Like, you know, back in the 1990s, when I was in grad school and John was in undergrad, one of the hot topics in those days was what's the computational complexity of natural language? Is there a reason it keeps cranking out like that?
I don't know. Peter, do you see the slides?
No, it went off.
Everything looks fine up here.
So try unplugging it and replugging it.
Blow on it also.
Well,
very 90s.
So we wanted to know what's the complexity of natural language? Is it a finite state automaton? Is it a context-free grammar? And this was very much approaching the phenomenon of human language from this very traditional theoretical computer science point of view of I've encountered something new and I want to know what kind of, what's its relationship to the other computational models that I'm familiar with. And that will help me to understand what this thing is capable of doing or not doing. So those questions were being asked about human language itself in the 1990s. And here we're interested in asking these same kinds of questions about transformers. So empirically, it seems like transformers are doing extremely well at modeling natural language. And so I'm very interested in, okay, well, what kind of a computational device is a transformer? And actually, that's a way easier question than asking what kind of a computational device is the human language faculty, because we actually know the definition of transformer and can think about it concretely instead of just kind of speculating about our own language abilities. And you know, older neural networks like RNNs and feed-forward neural networks, it's pretty established results, helping us understand how those kinds of neural networks relate to traditional computational models. And transformers are very interesting because they don't kind of fit into the models that you would learn about in a normal undergrad theory of computation class. So like they're not finite state automata. They're stronger and weaker than finite state automata. They're not context-free grammars. They're both stronger and weaker than context-free grammars. And they seem to cut across Chomsky hierarchy and these things that are traditionally taught in undergrad theory classes. But still, you know, it's a reasonable question to ask: what kinds of models can these neural networks be related to? And so in this talk, I'm going to be talking specifically about relating transformers to formal logic. And logic turns out to offer a lot more flexibility than things like automata or circuits that let us find things that are actually exactly equivalent to transformers. And some of these logics have been studied for years and years, and some of them are very well understood, some of them are less well understood. And it turns out that if you can show that a particular kind of transformer is equivalent to a certain kind of logic, you can sort of pillage the literature from logic going back for decades, you'll see, and take all of these results that are known from logics and transfer them over to transformers and get for free a bunch of really interesting results about transformers. There are also, you know, you look at the logic literature and look at the variations that they've tried to logics, and then you could say, well, they've done this kind of thing. What would be the analogous change we'd make to the transformer? And you can actually get ideas for ways of modifying transformers by looking at these logics that have been studied for a really long time. So there's a potential source of new ideas for new architectures here, some of which we've started to think about, and maybe there's a lot to be done there. Third possible benefit of this kind of approach, this is the most speculative. Logical formulas they're a formal language meant to be looked at by humans, right? They're symbolic and kind of sort of related to how people formulate natural language logical arguments, right? And or not. These are operators are modeled after things that are natural for us. So I'd argue that if you can show that a neural network is equivalent to a logic, then you could train up a transformer, preferably a really, really small transformer, translate it into a logic, and then you should have a human readable form of this transformer. And so I think it's reasonable to ask, could you use that human readable form of a transformer to understand better how that transformer is doing its thing? And this is very iffy, right? The translations turn out to be very, very inefficient. And so maybe there's still work that needs to be done in order to make this possible, but it seems like a stretch goal for this program of research. All right, so as a taste of the kinds of claims we'd like to be able to prove, consider Boolean formulas like this. So there's no variables, just have zeros and ones, constants, and ors, and nots. And so this is a pair of problems that to me is very striking. So we can prove that transformers can test the syntax of these formulas. So in order to make this formula syntactically correct, you just have to make sure the parens are balanced, right? That's the hard part. The ands, ors, and nots is easy to make sure they're in the right places. Checking whether the parentheses is balanced, this is a problem that transformers can solve. So we can prove that the transformers can do this, no matter how long the sequence is, no matter how deeply nested the parentheses are. So it's not an approximate solution. Transformers can check this exactly for all strings. So that's an interesting and at first to me a very surprising result. On the other hand, if you want to know not only whether these formulas are syntactically correct, but whether they're true, in other words, to be able to compute the semantics of these expressions, this is something that under reasonable complexity assumptions, we can prove that transformers cannot do this. Okay, and these two problems seem quite similar, right? Checking the syntax versus checking the semantics of these Boolean formulas. One is provably possible, one of them is provably impossible. So I think that's a cool pair of results, and you can analogize all you want about well-formedness of sentences versus checking whether or not they're factually true or not, or something like that. But that would be strictly in the realm of analogy. Yes.
Yeah. So I just wanted to clarify a little bit.
Yeah.
Like, you're not talking about a general purpose off-the-shelf transformer trained on human language,
right,
that could reasonably get.
That's right.
This is like specialized, trained under some ideal conditions.
That's right. So this would be not even trained at all. So you can hand construct the weights of this transformer, and then it can solve this problem perfectly. But I mean, that leads me to believe that if you train it on this task, then maybe you would be able to do it. Although there is a discrepancy there. There are some tasks where you can prove that a transformer can do it, but people have tried and failed to make a transformer learn how to do it. I'll mention another example like that later.
And are there like, I guess, do these proofs have like limitations on like either the width or the depth of the transformer? Or is it any like arbitrary?
Oh, yeah, great question. So I think maybe I'll answer some more of this general type of question later, but for this particular one, I think you need depth too.
Okay.
Yeah, and there's some width, but I don't know what the width is. Yeah, it's probably big if you just follow the recipes in the papers. Probably there's some more efficient way of doing it, but we haven't worked very hard
So
on it.
much smaller than the 12
Yeah.
layer, 24 layer.
Yes, yes. So two layers is all you need for this.
Okay.
Yeah, yeah. Yes, but then for here, so transformers might be able to compute this, like this formula is very easy to figure out whether it's true or false. So transformers, I'm sure, can be trained or hand constructed to do this up to a certain length or a certain depth of nested parentheses, but it's guaranteed under these assumptions, it's guaranteed that the transformers will fail at some point. Yeah, yeah. There's a question over here.
It was resolved.
Okay, great, great. Any more questions?
Are you going to get into a lovely grid where you talk about other formalisms and whether they can or can't test these things? Like,
No,
can finite state automata test?
no, that's a great idea, but no.
And yeah, I'm particularly interested if there's anything known where you can test. I think there are, right?
Yeah, context programmers can do this. Yeah, I assign that as exam questions sometimes. Yeah, so both these, like in Chomsky hierarchy, these would both be context programmers, and yeah, to me, it's interesting that they separate there. Yeah, yes. Sorry.
I'm sure you'll get into this later, but is there a particular reason why it's objective to do this with transformers instead of just like writing up some code with some rules and saying like with a state machine?
Oh, right. I mean, this is an easy problem, right? So, like, we know how to solve this problem. No, but I think that it's just interesting. So, to me, the can'ts are much more interesting than the cans, right? Because people aren't out there saying transformers can do everything. Like, you look on social media, like, people just like, are they going to be artificially generally intelligent soon? Are they going to be able to make scientists obsolete? Are they going to be able to, do all these things? And people are just like over the moon about all the things that they can do. And so, to me, it's really interesting that there are some very, very easy things that they cannot do. And this should be very sobering, right? They can't do this problem. That should be really, really easy. And so should we be trusting our, weapon systems to these things? And maybe not. Yeah. Until we can make them better. Well, maybe never. Maybe not. Yes.
So what is N here?
What's what? Oh, this is the sequence length. Yes.
So we understand like O, poly, and beta.
Yeah, right. So to do this negative result, you do have to assume that there's a limited precision being used to compute all of the activations of the transformer, as is done in practice. And so some people assume that it's just a fixed O1 precision. Some people do O log n precision. So the particular result I'm alluding to is making this very, very loose assumption that if you have n sequences you need to process, you allow yourself n to the k bits of precision, where k is any fixed constant number, which to me is like a really absurd amount of precision. So this is, to me, a very, very generous assumption. But even then, transformers aren't able to solve this problem.
So when we define like solve this problem.
Sorry?
So when you define like when you see like transformer cannot solve the problem,
yeah,
it means like we assume like we have arbitrarily long formula.
Arbitrary long formulas, yes. But one fixed transformer. So there's no one fixed transformer that would solve this problem for arbitrary lane sequences. Yeah. All right, any more questions? Okay, great. All right, everybody knows what a transformer looks like, right? Okay, but we're going to be looking, for most of this talk, we're going to be thinking about transformers as language recognition devices, which maybe is maybe a slightly old-fashioned way of thinking about transformers. I think these results should carry over to a more conventional language modeling setup. But we're going to be thinking of a transformer as the usual stack of self-attention and position-wise feed-forward network layers. And then at the top, we're going to take the last position, put a sigmoid layer on it, and we're going to get a single scalar out and use that scalar to decide whether or not we accept or reject the string. If you remember BERT, so when like BERT did binary classification of strings this way, or you could think of this as a language model where the language model has to answer yes or no, and this is the softmax output that is constrained to the vocabulary of yes or no. Yes. Okay, because we're just interested in yes/no decisions, and this is like a really, really traditional thing to do in CS theory of taking all kinds of problems you might be interested in and boiling them down to yes/no decisions about strings. Okay, What's probably less familiar is that logical formulas can also be thought of as string accepting devices. I will talk more about how the syntax of this works later, but basically logical formulas are true or false, right? And so I'll describe later how you can take a logical formula and you can interpret it with respect to a particular string, and then you can ask whether the formula is true or false. And so a formula also defines certain classes of strings. This particular one says there are more ones than there are zeros in the string. And I'll explain more about this syntax later. Okay, but this is the only point you're supposed to get out of this slide is that logics also can be treated as string accepting or string rejecting devices, just like automata can, and just like regular expressions and grammars can. We're interested in inputting a string and getting a yes/no decision out. Okay, so now that we've both fit transformers and logical formulas into this mold, then we can ask, well, what's the relationship between these things? And my student Andy commented to me, he recently gave a talk at, where was he? Kaiserslautern, no, Bochum University in Germany. He gave a talk to logicians, and he came back from this talk and he said, you know, the logicians really don't like what we're doing. They think it's really, really boring. They hate the translations that we come up with between the transformers and the logics because they're too easy. They're just syntactic manipulations. And my response to that is like, yes, I can see why logicians would not like this. There's nothing deep, there's nothing like really fancy that has to happen to go between these two worlds of transformers and logics. But to me, that's what's so cool about this, that the translation between transformers, which were designed at Google to do machine translation or something like that, and logics, which were designed for some other completely different purpose, turn out to be so similar to each other. And if you think about like the three main ingredients of transformers, so you have the word position vectors, the self-attention, and the position-wise feed-forward networks. Those are the three main ingredients, right? And if you think about the three main ingredients in a typical logic, you've got the predicates, and you've got the quantifiers, and you've got the Boolean operations, right? Quantifiers like for all and there exists. These are some funky ones, and I'll tell you more about later. Boolean operations, and or not, implies, if and only if. And these correspond in a very, very natural way. So in these translations, the word vectors become the predicates, and the self-attention become quantifiers, and the position-wise networks become these Boolean operations, and vice versa. So the translations between these are very, very straightforward. Yes?
So I totally buy your first statement. Are you gonna get into the second two?
A little bit, yeah.
It's totally not immediately obvious to me.
I'll get into it a little bit, but to really dig into this, I think you'd have to read the papers. Yeah. Yeah. So this correspondence is like so close that I almost feel like what transformers really are. There's lots of papers saying transformers are this and transformers are that. So if I was going to write a paper called Transformers Are blank, I would call it like transformers are learnable formulas of some temporal logic. And that they weren't designed that way, but that's really what they seem to me to be. All right. So here's an overview. I'm going to talk about two main groups of results. So the first main group of results is about a simplified version of transformers called unique hard attention transformers. Maybe some people are familiar with them, maybe not. They're not used in practice, but there's just kind of like a Mickey Mouse version of transformers that are easier to study. These turn out to be exactly equivalent to a very, very well-studied logic called linear temporal logic. And those in turn are equivalent to star-free regular expressions, counter-free finite automata, as well as first-order logic. So because this is a very well-studied logic, we get a lot of results from the logic literature that carry over to transformers, these kinds of transformers. The second group of results I'd like to talk about is of actual real transformers, so the ones that use softmax in their attention instead of this unique hard attention. And here we have to make some assumptions about the precision that's used in the transformers, which also makes them more realistic. So we're not embarrassed about these assumptions. And depending on what kind of precision you assume, then you get different kind of results. So if you assume like very high precision, I alluded to this already, there's a logic called first order logic with counting or first order logic with majority that is at least as expressive as transformers. This is a one-way result. If we assume fifth precision in a way that I'll make more precise later, then transformers are exactly equivalent to a logic called temporal logic with counting, which I will explain more about. And this is a fairly well-studied formalism. This is not. So there aren't nearly as many results to pillage from the literature, but but still, having the logic there makes it easier to prove theorems about it. So my student Andy managed to prove one particularly practically important result, which is that in temporal logic with counting, if you increase the depth of the formulas, you get more expressivity. And so it immediately follows from this equivalence that we were able to prove that in a transformer, if you add more layers, you add more expressivity. And this is something that you're not very surprised by this. We all thought that depth increased expressivity, but it's nice to have a formal proof that this is so, and to actually know what the language is that separates the depth levels. And
That's only for one precision, right?
only for fixed precision. Yes, yes. Okay, and there's one experiment in this talk. It's all theory, but there will be one experiment that confirms this finding.
Oh, sorry, fixed precision, which is
Yeah.
to say, that's
32 bits.
which is what we have.
That's what you use.
Alright.
Yeah. Okay, so unique hard attention. So we're going to prove that linear temporal logic is equivalent to unique hard attention transformers, but more than that, so LTL. So this is a logic, and people always want to know, like, what languages are in and not in this formalism. So the classic example of a star-free language, a language that's definable in LTL, is AB star. Everyone's familiar with this random expression notation? So this is epsilon, AB, AB, AP, and so on. The classic example of like a really easy language that's not in this is AA star. Okay, it's really, really easy. So you just have to test whether the number of A's is even, and that's something that's not definable in linear temporal logic. Temporal logic is good at detecting whether this comes before that or things like that, but it's not good at counting things. And the automata version of this is called a counter-free automata. So there's no the automata is not able to count the number of A's to see whether it's even or odd. Another example that's been really prominent in the transformers literature, as well as the theory literature, is parity. So you have a string of zeros and ones, and you want to know whether the number ones is odd or not. All right, and this example has been very well studied because there was some debate for a while about whether transformers could do this. Turns out they can, but no one has been able to make transformers learn them. So the parity is a very nice example of a language that seems to be expressible by transformers, but not learnable by transformers. Yes. Okay. So we're gonna show that this logic is equivalent to unique hard attention transformers, and more than that, I mentioned already. There are actually many different variations you could think of unique hard attention transformers, and these all correspond to variations of linear temporal logic that have been studied in the literature. So we're actually not going to get just a single equivalence, but we get a whole family, infinite family of equivalences.
So you can say what actually a unique hard attention transformer is.
Yes. Thank you, John. Here's what a unique hard attention transformer is. Okay, everyone knows how attention works. You've got oh, sorry, this is a mistake. So you've got a query and you've got keys. Sorry about that. And in softmax attention, the query computes all these logics and then takes the softmax of these logics, and you get these fractional weights that each position attends to, right? That's how normal attention works. Okay, so in unique hard attention, all of the attention goes to one single position. Right, and so you take the highest scoring logic. Okay, so first of all, there's masking. So this query does not attend to any of these keys. Okay, so that's no typical future masking or causal masking, but we're doing it strictly, so actually the query cannot attend to its own position. So that's weird, I acknowledge, and I'll have more to say about that. So we look for the highest logic that's strictly to the left, and if there's a tie, we choose the rightmost one. Okay, so properly, this could be called rightmost unique hard attention. All right, does it make sense? Okay, and this doesn't correspond to anything that's used in practice, but I don't know. It got introduced, I think, by Michael Hahn, and just has become a frequent topic of study. And it's nice because it turns out to be equivalent to this very, very well studied class. All right, does that make sense? Unique hard attention. Okay, here's what linear temporal logic looks like. What time do I have to stop? Like hard stop at 12?
11:55.
Okay, all right, I'll go a little faster.
Done it.
Yeah. Okay, all right, so here's how temporal logic works. So this is a predicate QA, and everything in linear temporal logic implicitly depends on a position of the string or a time. This is temporal logic, right? So about time. So you could sort of translate this formula into it is now A, meaning it's A at the current position. Okay, I don't know what Q stands for. So here we have a string AB, 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 and then I've written 1 or 0 depending on whether the formula is true at that position. And then if you want to know whether the formula is true of the string, we look at the last position. Okay, so that I've written that in blue. So this formula is false for this string. QA is true for this string, and it is false for this string. Make sense? Okay, so QB is the same, except we're looking for B's instead of A's. All right, and where it gets more interesting, we have these temporal operators that kind of play the role of quantifiers. So you're familiar with for all, if there exists from first order logic, well, temporal logic has these letters that function as quantifiers. So P stands for previously or past, and it means it has sometimes been A in the past, right? At the present time or sometime in the past. So you see that it's true here because it's A right now, but here it's still true because it was A at some time in the past. Okay, and it's true of the whole formula. So basically, this formula is going to be true if there's an A anywhere in the string. So it's true for all of these strings. Okay, it has sometimes been B and it was A before that. So this is at some time in the past, it was true that it was QB, and at some time before that, it was QA. All right, so this formula is going to be true whenever there's an A somewhere in the string and a B somewhere in the string afterwards. Okay, so it's true for this string, it's not true for this string because all the A's come after all the B's. And it's true for this string.
Sorry. Oh, it was true in the past that it
Yeah.
was QB right now.
Yes.
In the past, it was QB right now. And
Yeah. Yeah, my English translation might not be like not super, but when something occurs inside the scope of the P, then oh, okay. Well, last time it went out and then it went out for good. Yeah, so this QB refers to a time in the past because it's inside P. And this past means it's like a past, like pluperfect. So this is a past before the time that's. I don't know. Okay, so this is a since operator. It has been B since it was A. All right, so in this string, this is kind of a hard one, but it's an important one. All right, so it's true here because there was some time at the present or the past when it was A. And ever since then, at every time step since then, which could be a zero number of steps, it's been B. So this formula is true.
that's true because it was never A.
What's that?
Is that true because it was never A?
At this time, it has been A.
Oh,
Yeah,
but it has to
this
be
time.
since, meaning since,
Yeah.
meaning afterward?
Yeah.
And since there's no
After that time, yeah, exactly. Okay, by contrast, here, the QB since QA is not true because it's never been A before, so this is false. Okay, all right, so then you can nest these things. So H stands for historically, means it's always been A. So this is, it has been B since it had always been A. Okay, and this is what you probably know more familiarly as like A plus B star. So one or more A's followed by zero more B's. And in temporal logic, we write it like this. It has been B since it had always been A. And so, okay. So it's true in this because you'd see the zero or more A's, one or more A's followed by zero or more B's. All right, any questions? My collaborator, Dana Englund, hates temporal logic. I'm not, she finds it so counterintuitive to read and understand these formulas. Yeah, so there's this other language that we prefer working with called RASP or BRASP, which is used as like an intermediate language in these proofs. And Dana always takes the opportunity to complain about how hard to read these are and how much easier RASP is to read. But that's what LTL looks like. All right, there's a whole bunch of operators. A U operator for until, F stands for finally, means same as P, but in the future. G is same as H, but in the future. X means at the next time step. Y means yesterday or at the previous time step. And there are a couple of others, but these are the most common ones. So LTL is the logic that has all these operators. But it turns out that S and Y are all unique. So the logic that has S and Y is just as powerful as the logic that has all of these. And it turns out that there's a variation of since called S prime or strict since. And you don't need to know the details of it, but actually this one operator is enough to give you the power of the whole logic. Okay, so I'll very briefly go through this direction and then in this direction. Yeah. All right, so we want to convert a formula of LTL into a unique hard attention transformer. It's a big giant proof by induction on the structure of this formula. And the name of the game is for every subformula of this formula, we want to make somewhere in this transformer at some layer in some coordinate of this vector, we're going to compute the truth value of that subformula. Okay, so at some layer in some coordinate that is dedicated to each subformula of that. And we build up this transformer inductively until we end up with a transformer that computes the value of the whole formula.
Are you making any kind of assumptions on the nonlinear part of the feed forward bit, or?
We use relus.
Okay.
Yeah. I think in nonlinear you should do, I think, but we use relus. All right, base case. So the simple predicate, so these QAs, those translate directly into word banks. right? If I use a one hot vector as the word embedding for A, what is the meaning of that vector? There's a coordinate in that vector that's one exactly when the symbol is A, and that's exactly what this formula does. This formula is one when the symbol is A. So one hot word embeddings correspond exactly to these guys. So the Boolean operators and not are computed by the position-wise feed-forward networks. And John, you've asked a couple of questions about this. So this is like a from the 1970s, 1980s, people figured out how to compute all the logic gates, like the XOR problem, right? So they figured out how to do and or. They figured out how to do and or using a one-layer perceptron, one-layer feed-forward network, but they couldn't do XOR. And so there was some kind of crisis in the field, but then someone said, oh, well, if you use two layers, you can do XOR. Sound familiar? Yeah, super old neural network history. But yeah, so this was one of the earliest questions people asked about feed-forward networks is what kinds of Boolean functions you can compute.
Is sharp there just a different symbol?
Yeah. Yeah, this must have come from another example where it was like A's followed by pound followed by B's. All right, turns out you can compute any Boolean function using two layers. Okay. Then the most difficult and interesting step is if I have temporal operators like this strict sense operator, then I need the temporal operators are all about relationships between positions, right? So I can't just use the position-wise functions to do this. I need to somehow use attention to look across the positions to figure out did this event occur before this event or whatever. So we use the temporal operators to we use self-attention to simulate the temporal operators. And here I think that there's no, so I kind of punted on this. And if you're interested in how that translation goes, then I'll refer you to the paper for the details of how to use unique hard attention to simulate the sense operator.
Are you doing anything interesting with the V matrix?
Like I said, the logicians don't like these translations. No, there's nothing super deep about
Sorry,
it.
are you doing anything? Are they just like
the V matrix? The V matrix, I don't think it does a whole lot that's that interesting. Yeah.
Okay.
Yeah.
And you're not bothering with things like layer norm.
In this paper, there's no layer normalization. Would it affect it at all? Every activation, residual network connections we use. Yeah, in fact, without the residuals, I don't know what we would do. Yeah, it might be less powerful. So everything in this transform is either a 0 or a 1. So if you threw layer norm at it, then you would just change it so that everything was either -1 or +1. I'm sorry, true would be represented by +1 and -1, and false would be represented by -1 and +1. And then layer norm wouldn't touch anything, and then you would everything would just pass through the layer norm. It would have no effect. Yeah, so this result should still be true with layer norm. I don't remember if the paper talks about it or not. I think it does.
Position embeddings?
Sorry?
Oh, position embeddings probably have to
So currently we don't use any position embeddings.
What are the parentheses are you doing?
Though, what?
Well,
So no, this is not the input string. This is the formula we're trying to simulate.
yeah.
Yeah. Yeah. Later we'll treat that as a string. Yeah. So in this result, this base result, we are not using any position embeddings. All right. So that was that direction. Now for this direction. So again, it's this giant proof by induction. So if we're given a unique hard attention transformer for every layer, okay, so this is kind of weird. So every layer, this a vector that depends on position. For every possible value of that vector, okay, we're going to construct a formula that's true if and only if that vector is that activation is equal to that particular value. Does that make sense? So there's a lot of these formulas. So okay, this transform only has 5 layers, so there's only 5 formulas, but 5 times the number of possible values that each vector could have. Okay, so it's 5 times like a trillion or something like that. So this formula could get very large.
Great.
Does that make sense?
The values are basically bounded the precision of the node.
Well, we have not explicitly bounded the precision of this, but as part of the proof, so this is kind of on the next slide, as part of the proof, you can show that only bounded precision is needed for this particular kind of attention.
Well, otherwise you have an
Infinite number, right. So the fact that this is finite is because this is a cartoon picture of how unique hard attention works. Each position only attends to one other position, unlike soft attention, right? So the unique hard attention, every position attends to one position, and because of the residual connection, each position depends on itself. So each vector depends on 2 other vectors, and because of this fact, you can prove that there's only a finite number of word embeddings, right? And then as you go through the network, the number of possible values that each vector could have gets bigger and bigger, but is always a finite number. So this is a consequence of the fact that we're using this very simplified attention. Okay, so that's that direction, transformers to LTL. Now, so here are some variations on unique hard attention transformers. So far we've done strict masking, and I kind of glossed over this fact, but we were actually doing both future and past masking. So future masking is what you're used to. Past masking is where each position can look at future positions. It's kind of weird. All right, so then the first question anyone who's used to transformers would ask is, well, that's weird. So what if we get rid of past masking? Does that make the transformer less powerful? So the answer is no. Oh, sorry. So that's what I just showed you. So the answer is no. It was a paper in 1980. I was born in 1976. This is a really, really old paper by Delgavai et al. They proved that temporal logic is no more or less powerful whether you use the future and past operators versus just the past operators. They have the two logics have the same power. And so as an immediate consequence, these two kinds of transformers also have the same power, because the correspondence between the logic and the transformer is so close. You get rid of the future operators and the temporal logic, you get rid of the past masking of the transformer. So these two transformers are equivalent. Okay, next question, someone who's used to real transformers would ask, well, the strict masking is really weird. We always let each position attend to itself. So what happens if you use non-strict masking? Does it get more powerful? Does it get less powerful? Turns out it gets less powerful. So the arrow is always from the less powerful to the more powerful formalism. And so this was studied in 1997. So that's newer than 1980, but still pretty old paper. So in 1997, they realized that if you take the strictness away from LTL, it becomes less powerful. It recognizes a class of languages called the stuttered Hungarian star-free languages. And so as an immediate consequence, we get that non-strict masking is less powerful than strict masking. Again, this is for this hard attention transformer. Okay, but this is a very surprising fact because this is what we do in practice. This is some weird thing that we concocted for this paper, but it turns out this is better. So in 2000, I guess we're going chronologically here. So in 2000, these two guys established a since hierarchy. They showed that if you have a formula of depth 2, it's more powerful than a formula of depth 1, which is how deeply nested the operators are. 3 is more powerful than 2, 4 is more powerful than 3, and so on and so on. And so it immediately follows the same thing is true for transformers. You add more layers, you get more powerful. I can't remember what the separating language here is. It's something very, very simple, but I can't remember what it is. All right, what about position encodings? So if we take this and we add position encodings, if you remember, I had a big picture where I said that the word and position vectors correspond to predicates. So the word embeddings, like this, the word predicates correspond to the word embeddings. So position encodings correspond to position predicates. So we need to add position predicates to our logic. And so if you want to add like sines and cosines, just like the original paper, that corresponds to adding a certain kind of predicate called modular predicates to the logic. And this was pretty well studied, but we're not going chronologically. So in 1992, there was a pretty famous paper showing that first order logic with these modular predicates, which is the same as LTL with the modular predicates, is equivalent to exactly the regular languages in AC0. Now, AC0 is a circuit complexity class. Maybe some people have studied circuit complexity. You did? Oh. Oh, okay. I mean, I never learned them in school, but people do the complexity there, yeah, seem to be very familiar. Yeah. Okay, so this is a well-studied class of languages corresponding to the sine and cosines. When I first saw the transformer paper, I don't know what you guys thought. When you first read the attention logic paper, I saw those sines and cosines, and I thought that is the weirdest thing I've ever seen. And I don't like this paper because that's weird. And the more and more I thought about it, the more I realized sines and cosines actually make a lot of sense, and it actually correspond exactly to this like very commonly used kind of predicate in logic. I'm continually amazed at how parallel the development of these two things was. If you want to allow arbitrary position encodings, subjects to this constraint, if you want the position to be a finite number of possible position encodings, then this corresponds to a logic called FO-MON, which is first order logic with all monadic predicates, and that was studied in a paper from 2005. All right, so the take-home message from this is once you've got this one equivalence between a transformer and a logic, you actually get this whole web of results that results from results that are established from the literature. Okay, any questions?
That's my question.
Okay, great. So if we want to model soft attention transformers, which is what we actually use in practice, so this matters much more, we have to consider logics that have additional abilities for counting. So we're going to take our temporal logic. So this is the same QA as before, and we're going to add this pound left operator. And what this operator does is it counts the number of times that something was true. Okay, so you can think of this as the number of times it has been A. So this is not true or false. This is a number now. Okay, so for example, if my string is A, then this will count 1, 2, 3, 4, 5, 6. And when evaluated on the whole string, it gives back 6. This gives back 3 because there's 3 A's. This gives back 3 because there's 3 A's. Does that make sense? Okay, we can also add and we can compare these numbers. So now this is a true-false formula. This says there have been more A's than there were B's. And this is also known as the majority language. And if you're familiar with the Chomsky hierarchy, then you'll recognize we're now beyond regular languages. So this is not a regular language. Okay, so A, that's true. A, maybe that's false because this is a strict inequality. It's not a great example, so that's also false. But like A, B, then this would be true.
Wait, yeah, that's wrong, right? That should be
It's wrong.
1, 1, 1, 1, 0.
The last, yeah,
This is wrong. More A's than
There's
B's.
more than A's than B's.
like at position 5, you have
Yes.
more A's than B's.
Yes, thank you.
It's not just
I thought I got rid of all the mistakes, but I got rid of like 3 or 4 mistakes this morning, but I missed one. Okay, thank you. All right, for a fancier example, this is the temporal logical counting formula that matches parentheses. So this says the number of closed parentheses is greater than the number of open parentheses, which is bad. We don't want that. So then this says that should never happen. Okay, and once you get to the end of the string, the number of open parentheses should equal the number of closed parentheses. All right, and that turns out to be necessary and sufficient to get all the parentheses to match up. So this is the formula that defines the deep language, the language of all the matching parentheses. And you can see that it has depth 2. You see I've got a counting operator in essence, not a counting operator, so that's depth 2.
I think there's also an error there. It should be at no time more right parentheses than left parentheses.
What? Yes, thank you. Yeah. The formula is right, English is wrong. Yeah. Okay. All right, for me, it was a surprise that this formula was so simple to do something that I've grown accustomed to thinking that, oh, this is hard because it's not a regular language. All right, so here are the results that I would like to go through. All right, so here we have a bunch of variations of transformers. So O1 means fixed precision, like 32 bits or something like that. The oldest paper considered no masking, and then the later paper considered masking. And then there's another paper that considered transformers with polynomial number of bits. Okay, and then we have 3 logics. So this is the logic that I just showed you. Here's the same logic, but the counting just counts globally. It's not to the left or to the right, it's just globally. And this logic has addition and multiplication in it. Okay, and this language class is more commonly known as uniform TC0. TC0 is another certain complexity class. Okay, so these transformers are less powerful than this logic. These transformers are exactly equivalent to this logic, and these transformers are less powerful than that logic. And then some example languages that do or don't fall into these. The majority belongs to this class. The deep language belongs to this class. That's the matching parentheses. I mentioned parity already, so parity is in there, but not in there. And evaluating Boolean formulas. So this Boolean formula value problem is believed not to be in there.
Wait a second. So if unmasked O1 precision transformers are strictly less powerful, that's to say like BERT is less powerful than like XLM. No, sorry, that's BERT also. It's less powerful than an autoregressive model.
Yeah.
Like formally.
Yeah, that is interesting. So to be more careful, you'd have to also think about the position encodings.
Yeah.
So these I think we're both not considering position encodings.
Rope is more or less powerful.
Well, I know we have that all about rope, which is a great thing to think about. So BERT only has position encodings up to a maximum length, 512, right? And then past that, it has no more position.
Yeah. Well,
So I would be willing to bet that BERT's actually less powerful than a decoder model.
but you can put the same constraint on the decoder model than they do in practice prior to rope. Because you still need to have a
Yes.
if you're going to
Right. But what I mean is that's as good as not having any position encoding at all. Because the position codes only go up to a certain number, and so past that, then you have to go without position encodings, and these results are for without position encoding. Yeah, I think I feel pretty safe saying that the decoder only model is more powerful than the encoder only model. Yeah, but yeah, maybe I'd have to think about it a little bit more to be positive. I think that's right. Okay, and then the separating language should be this deep language, but I don't know how well a decoder only model in practice learns deep. That's an interesting question.
Language?
What?
What is the separate?
I predict that like a GPT style model could learn deep, but BERT could not. So you could do an experiment to see if that's true or not. I don't know. I don't know if it's true or not. Okay, so I'm short on time. I'm going to skip past this. This was a fun paper to write, but you don't need to know it. The only reason I'm mentioning this paper number 7 is just because I wanted to back up the claim I made way at the beginning of the talk that transformers seem not to be able to evaluate Boolean formulas. All right, I'd like to focus on this pair of results. So to go from discounting logic to transformers, what does this look like? Now let me qualify what I mean by fixed precision. There was some skepticism when I first mentioned it. So if a number has p bits of precision, let's just say it has 1 sign bit, p over 2 integer bits, p over 2 fractional bits. And the fact that this is split half and half is not terribly important. And whenever I do a basic operation, we round the result. So addition, multiplication, square root, x, these operations are all rounded to the nearest number, which is exactly what we do in practice. Now here's the weird part. We're also going to treat this as a basic operation. So inside attention, so in the numerator, the softmax gives you a summation over all positions in the denominator, and then the weighted average gives you a summation over all positions in the numerator. And if you add, n could be really big. The sequence length could be really big. If you have a fixed amount of precision, that sum could overflow. So some people say, no, you shouldn't do fixed precision because you just can't even compute attention that way. Something bad is going to happen when you do attention. So there are various ways to respond to that. In this paper, we're saying, okay, we're going to treat this div sum operation as like an atomic operation, perform it exactly, and then you round the result. Okay, and that way you can actually do attention. If we didn't do this, then some overflow would occur here, and some overflow would occur here. All right, and this assumption is important in order to make this result go through.
Is this in practice? This is not an issue.
In practice, it's not an issue because the sequences probably don't ever get long enough to make it an issue. But it would be interesting to think about what really does happen.
Oh, like you could have explosion if you were over 10 million things you were summing up and just the numerator blew up suddenly.
Yeah, sure. But you have to think very carefully about exactly what operations get done. For example, when you do softmax, you do all this log some x type trick, and I don't. Yeah, I'm not sure. And a lot of it might depend on like internals of the GPU implementation that might be trade secrets. I don't. So I feel that this is like a fairly reasonable thing to do, but it's not obvious, and so this is important that I say this. Okay. So it's a giant proof by induction. So for every formula, we're going to make a coordinate of a layer of this transformer, compute the truth value of that subformula. So the interesting part of this is, you said I have to stop at 11:50 or?
No, yeah, just the whole talk has to be done at noon, so nobody has any questions.
All right, because you guys are asking your questions as you go, right? All right, but I'll speed up. All right, so to do this counting operation, we use uniform attention. If we want to know how many times something occurred, we just uniformly attend over all those positions, and that should let us count up the number of ones that there are at those positions, right? Something like that. The problem is attention does not count. It averages, right? In this case, it's a uniform average because we're doing uniform attention. So if I've got like some formula phi that's true or false, if this is 1, 2, or 3, the best I can do here is I cannot compute the number of times that phi has been true. I can compute the number of times that phi has been true divided by 3. And if I'm at position 1000, the best I can do is I can compute the number of times phi has been true divided by 1000 or 1001 or something like that. So that's fine. If you want to compare two numbers, it's fine if everything's scaled by a constant. If you want to add two numbers, it's fine if they're scaled by a constant. So this scaling is not necessarily a big deal. But if you think about, if I have to compare two numbers that are very, very close, right? 1000 divided, like 1 over a million compared with 2 over a million. I might find myself needing to compare two numbers that are very, very close together. And that comparison function looks like this, right? False, 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 true. And as the sequence length gets bigger and bigger, as the numbers I need to compare get closer and closer, that slowby part might need to become more and more slowby. Does that make sense? In order to tease apart numbers that are very, very close together. And that turns out to be really annoying and hard. So in fact, there's a theorem that says that under a certain reasonable set of assumptions, transformers are Lipschitz continuous, so they have a bounded derivative. But here I'm arguing that in order to do this comparison, you need a possibly unbounded derivative right there. All right, so this is a problem, and this problem comes up in a lot of papers in the literature in different guises, but this problem is like very pervasive, and there are lots of, frankly, hacks to get around this problem. So we have to go hunting through the transformer to look for little bits of the transformer that actually are not Lipschitz continuous. So the two most promising ones are layer normalization. So layer normalization looks like this. And if you graph it in 3D, it looks like this. So it has this nice step function, step shape, and you can exploit the step shape to get the job done. Okay, is that true? Does layer norm look like that?
What is E?
Expectation, average.
Square and the bigness of variance?
Uh-huh. All right. So if you're like deeply familiar with transformer internals, you know that there's a plus epsilon here to avoid division by 0, or to avoid dividing by some very small number. You throw in that epsilon, then this vertical wall here becomes sloped, and then the proofs get ruined. So there are some proofs, including some of ours, that rely on the fact that we're going to use layer norm, but we don't want that epsilon there. The original paper did not have an epsilon, but if you look at PyTorch's implementation or something, there's an epsilon there. So it's kind of embarrassing that we have to depend on such a minute detail. There are other papers, including one of ours, that use the rounding function. So if we're working in fixed precision, then you have to round numbers, and the rounding function has this staircase kind of shape. So you could use this. You could exploit the fact that rounding is not Lipschitz continuous to get you what you need.
Isn't that exactly
Also not beautiful.
for the layer norm? Is that exactly the point? The thing that you're trying to tease apart is those numbers that are very close together. When those numbers are very close together, you have a problem with doing layer norm.
Yeah.
And that's where the epsilon gets added.
Yeah. Right. So like both of these things are playing very close to like a lot of things that like very close to the hardware kind of issues that we'd rather not be thinking of. So these are hacks. These are not beautiful solutions. And so what that means is in practice, so if we make some claim about this formula, this logic being included into this transformer, in practice, we're going to expect that things will start to break down in practice for really long sequences. But that surprises no one, right? Like we know that things are always going to become bad when the sequences get really, really low. So I don't know. So this is not the end of the story. But yeah. Okay. So other direction, to go from the logic to transformers, go very fast to that. No, we want to go from transformers to logic. So for every bit of every activation, we want to construct a formula that's true if that bit is set. And I'll skip this. The long and short of it is, if we have to do this div sum operation is the hard part. If we want to add up a whole bunch of numbers, but they have a fixed precision, it turns out that you can use this logic to do this. Even though the number of numbers might be very large, but the precision is fixed. So a finite formula can do this. And then we have to divide. And if you do like do you remember this from grade school? But you did it in base 10 instead of base 2. So you can do the grade school algorithm for log division in this logic also. And crucially, we only need to get the first p bits of the answer. And so there's a finite formula that will do the grade school division algorithm up to p bits. So we can do all of this in p bits of precision using a finite size formula. All right, that's all I have to say about that direction. And oh yes, last thing I want to talk about. So there's this logic that we've now proved is equivalent to fixed precision soft maximum tension transformers. And unfortunately, there's not a vast literature about this logic. They were invented relatively recently. Well, no, we invented the logic. The bidirectional version has been studied in the literature, but not a ton. So we had, instead of saying, oh, I've got this result from 1980, we said, okay, in 2025, we're going to prove our own results. So Andy managed to prove that in this logic, depth 2 is more powerful than depth 1, depth 3 is more powerful than depth 2. What's very striking is the separating language is really, really simple. So it's just A plus B plus. So one or more A's followed by one or more B's. Or one or more A's, one or more B's, one or more A's. And the number of blocks is the number of layers in the logic that we need. Okay, seems like it should be a really, really easy task, but you need k layers in the logic to recognize k blocks of letters. And that implies that you will need k layers of transformer in order to recognize k blocks in the language. Does it make sense? Okay, I don't know if that accords at all with your intuition of using transformers in practice. To me, this seems really, really weird. So we did an actual experiment, the only experiment in the in the paper. So this is on language modeling rather than binary classification. So everything gets shifted a little bit, but this basically make the same prediction. So in order to recognize k blocks of letters, you need k minus 2 layers of the transformer. All right, so the x-axis here is the depth of the transformer. Y-axis is the language that we tested it on. We trained on shorter strings and tested a longer string. So we were interested in how well do these transformers length generalize. And the colors and the numbers represent how well the transformer actually did. So the theoretical prediction is this staircase here. So the theoretical prediction is everything above the staircase, transformer should be able to do. Everything below the staircase, transformer should not be able to do. And I think this fit is incredible. Like it's not 100 and 0, but you see there's all these hundreds here. It's just, let's just look up there for now. So there's all these hundreds here. And yeah, I mean, the transformer is going to get it sometimes, but these are all, pretty bad numbers. So there's nothing above 70 here. So to me, this is like very, very striking confirmation of the theoretical prediction.
You're putting in a six vocabulary plus thing and just trying to see if that's accepted or not.
6 vocabulary?
Sorry, when you're the L3, L4, this is A plus
A plus B plus A plus B plus. It's just A and B is, and the string is the
and
vocabulary.
just trying to see yes or no. And just training using just standard whatever.
Yeah, no position coding, future masking.
No position.
No position.
Doesn't that mean that so an A plus B plus is the same as just a bunch of interleaved days and things, right?
No.
Why?
Because the transformer is autoregressive, so it actually can recognize interleaved A's and B's. Like it can say after every A there's a B and after every B there's an A. So the language modeling versus classification is slightly different. Yeah. But anyway, so the theoretical prediction matches very closely. Once you get down below here, things start to get worse. But we say, well, this is not our fault. This is because the transformer is not able to learn it. So maybe we didn't train it long enough. Okay, I guess that's our fault. Maybe the width of the transformer is not enough. Maybe there are other factors at play. But the fact that the transformer is not able to learn this is not surprising. In theory, we can definitely write down the transformer that does it. But just if SGD is not able to find it, that's kind of a separate question. But the prediction definitely is that transformers will fail below this line, and nothing comes anywhere close to perfect below that line. All right. Oh, animation. Wow. Okay. All right. So to wrap up, the take-home message is that logic is a really great tool for studying transformer expressivity. People have also looked at automata. People have also looked at circuit complexity, but logics really seem to be an extremely, extremely good fit for transformers. And I don't know, there's a lot more variations of logics that let you match the properties of the transform more closely. Especially temporal logics turn out to be an extremely, extremely good fit for transformers. So if you find this topic interesting, then I recommend this particular approach, and more people are adopting this kind of approach. We've established an exact equivalence between the simplified kind of attention and simplified kind of transformers and LTL. LTL is a super well-studied logic, and we were able to mine lots of results from the LTL literature, bring them over to the transformer side, make a lot of interesting conclusions about transformers. With softmax attention transformers, we're also having a lot of success with the logic that we've proven equivalent to. Unfortunately, it doesn't have nearly as much existing literature, but we are able to make predictions based on the logic that carry over to the transformer, like predictions about depth, and we're able to confirm those predictions by experiment. So that is all I have to talk about. Thank you for your attention, and I'll be happy to take more questions. Oh, sure.
Have you explored how expressivity changes with different nonlinear activations, particularly gated linear units, SWIGLU? Seems to be a correct parallel with logical operations.
Okay. No, I've not explored any other activation functions. There are a couple papers that use GELUs, and they use GELUs to approximate multiplication. So I'm not able to say too much about it, other than mostly the feed-forward networks are like there's universal approximation theorem for feed-forward neural networks. For Boolean functions in particular, you can express any Boolean function exactly. And so ReLUs seem to be powerful enough to do whatever we want them to do. And so we haven't paid a lot of attention to other kinds of activation functions, but I think that would be worthwhile to look at those alternatives. But no, haven't done it. ReLU is super convenient because it doesn't involve any exps or complicated irrational numbers, transcendental numbers, or anything like that. ReLU is very, very convenient and mostly does what we want it to do. But yeah, I think that'd be interesting to explore more. Yeah.
Do you have any practical recommendations from the bottom right of your matrix?
That's a good question. So I think we need to do more thinking about what kinds of real world phenomena look like these languages. So a lot of other people working in this area have looked at something like called the K-hop induction problem. So induction heads are something that are believed to be the mechanism driving in-context learning. So like if you ask like, what's the capital of Uruguay, then somewhere in the context it says the capital of Uruguay is whatever, and you need to look up what's the word next to Uruguay, something like that. But then if you need to do some multi-hop reasoning, like what's the population of the capital of Uruguay, then you need to look up capital of Uruguay and the population of that city. And so people have done studies about K-hop induction and tried to argue that that's something that would be practically useful. I'm not sure off the top of my head how this A plus B plus language relates to anything practically useful. But it has a similar kind of feel, right, to K-hop induction. Just involves hopping around more. Yeah.